Good morning, folks. How are we doing today? Good. One person is good. Everyone else, a mystery. Mystery unknown to mankind. I hope we're doing great. Today, we are going to continue in our adventure into coding up multiple shooting. And let me pull up the notes from last time here. All right. Okay. All right. Let's go here. Wonderful. So we were coding up multiple shooting, and we were like right in the middle of it, kind of near the end, and we were about to do a multiple shooting optimization for our drag race problem. So just a recall, okay, just as a memory, we have the idea of a multiple shooting approach, a formulation for trajectory optimization, is so that way you can break up instead of doing one simulation across your state over time. That's single shooting. We break it up into multiple shots. One, all those different shots, okay? Now the RAW, the RAO, the RAW text on the Canvas page really does a nice job of laying out the various methods that people use, including multiple shooting for setting up trajectory optimizations. But the key part here, and again, I'm going to keep beating the bush on this, is that once you start moving from single shooting to then multiple shooting, you start introducing things called defect constraints. In multiple shooting, a defect is the difference here between the end of one shot and the beginning of the next. And the beginning of the next is defined by a decision variable. Okay? In direct collocation, the defect constraint has to do with the curvature of the spline that we talked about on Tuesday. Okay? So by the way, feel free to download the code if you didn't follow fully along last time. That we have the exact code that I did from last time. It's up on the Canvas page for those who are on the Zoom right now. So go pull that up. All right, and let's go here. So where were we? Here's our MATLAB, my friends. Good old MATLAB. So the scripts that you want to have open are drag race multi. This is our multiple shooting drag race problem. Okay, and its job, all it is, it's just have to set up the optimization problem, so that we set up a cost function, our decision variables, and our constraints, and we throw it into our optimizer fmin_con. Okay, that's all. This is our outermost script. In fact, it might be helpful. Let me go into pull this back up here. The structure of our code right now. So here's our code structure. We'll pull this up here. Our code structure. Our main script is our drag race multi. Okay. And sometimes it's helpful just to be like, oh, look, here's that's our main script, right? This is just how we structured it, so that way you can follow along what we've done. Okay. And it also made me remind yourself, because it's been a week. And I know I'm sure all of you obsessively rewatched the lecture from Thursday. I mean, why wouldn't you? What else do you have to do with your time? Okay. All right. That's your main script. And that main script is going to then call our optimizer fmin_con. So if you have trouble setting up your code for when you're doing trajectory optimization, it might be helpful to think about the structure of the code. That's fmin_con, and that's our optimizer. So this calls fmin_con. What does fmin_con need? Well, my friends, if you're ever confused, you just go back to MATLAB. You say, oh, help, fmin_con. Okay. Well, we're going to be using nonlinear constraints. Okay. So that means we have to use this version of fmin_con right here, where we give it a cost function. We got to go all the way up to having nonlinear constraints. We can give it all this other stuff if we have it, but you need to give it nonlinear constraints. So we need to call some cost function. We call it function. Now that's super easy. Our cost function is so simple. We're trying to minimize time on this drag race. We're trying to see how fast we can get from one point to the other, right? So it's just time. So it's just time. So it calls our cost function, right? And we have to call our constraints non-lcon. Now, in our code, we called our non-lcon, we called it non-lcon multi. It's a whole new script file, a whole new function file called non-lcon multi. Okay, just because it's a multiple shooting, it's our nonlinear constraints for a multiple shooting. Okay, all right, we have to call that. But in order to run our nonlinear constraints, keeping in mind, we have to move this block from here to here, okay, which means we have to simulate, right? Okay, we're doing shooting methods, which means you have to simulate. Shooting means simulate. Collocation, don't simulate, okay? All right, so what do you need to do? You have to, let's go back to the full screen here. So in order to assess your constraints, you're going to have to do simulations, right? You have to know if this shot ends up where this one begins. So you have to do simulations, right? So we have a simulation script that we made, okay? And our simulation script was called, we called it simulate multi. I can't see that right there. Simulate multi. So simulate multi is what non-lcon multi calls. Okay. Well, if we're doing simulations and we're doing time marching integrations, what are our methods that we've covered in class for those time marching integrations? There was Euler's method, and in MATLAB you have a commit for a variable time step Virunga-Kutta method. It's called ODE 4.5, right? So simulate multi calls ODE 4.5. ODE 4.5, right? And then ODE 4.5 calls your ODE function, which I called ODE 2. All right. Right. That's the structure of our code, right? Just laying out what all of our functions and scripts are, right? And if you want, you could lay out, hey, what do each of these things pass back? Well, our ODE function, as we covered in homework 1, don't forget about homework 2, due next week. It's a much simpler homework. People were kind of flying. Some people are already flying through it, but do not let that lull you into false sense of security. Okay? You never know. Okay? You could pass it back with a little arrow right there. What does it send back? Well, your ODE function has to send back the derivative of your state, dx. Okay? That's what it's always sent back. ODE and ODE 4.5 is going to send back some vector of time. We call it t out and x out. That's our trajectory, right? Now simulate multi. It needs to send back, what do we want to send back here? The final, it says it's sending back the final position and the final velocity. It wants to know at the end of its shot, what are the states? Okay? So it sends back the, let's just say the states at whatever the final time is. So we'll just say our states, you can't see that. So it sends back our states at our final time. Give me a second here. So what we're doing is this so that way you can follow along what we're actually up to here. All right. So that's gonna and those states at the final time. Then we have to turn back into our nonlinear constraints. So here's non-lcon multi. Okay. All right. And that's going to send back G and GEQ. So that's going to send back here G and GEQ. Recalling that G is got to be less than or equal to 0, and GEQ has got to be equal to 0. So all of our defect constraints, they are equality constraints, saying that these two things have to line up. They're going to be sent back as these equality constraints. And that's where we were finishing up coding. We had actually coded correctly, we think, all we send it back to ODE 4.5. We're able to simulate little shots. This was an important part of simulate multi, that we give it a time, so you can't see that. that we have to give, that simulate multi, we put in a time span, okay? And that's important because our time span is not going to be the entire length of the trajectory. It's just going to be these little shots. We have to tell it, hey, what's the length of each of these little shots, right? Okay. All right. So we have that's done, that seems to be done. Now we're on non-Elcon multi. We got to work on that. Yeah, we didn't finish that last time. So let's go to non-Elcon multi. So let's go to non-Elcon multi. All right. And we set it up so we have a final position. It's going to tell us where we want to land, where we want to end up. We have no nonlinear inequality constraints in our problem. Recall we're doing defect constraints and also final condition constraints and initial condition constraints. Okay, so here we're going to loop through each of our shots, okay, and compare to the start of the next shot. Go right there. So for iter is equal to 1 colon number of shots. It's going to simulate given W. Give me a second here. I'll think out loud here. Send in W, W end. Ha. One thing we got to change is I'm spotting one error. I'm right now in simulate multi. We've tried to figure out how many points there are in our spline n, okay? And for our previous single shooting methods, that was easy. We would send in a decision vector that looked like this, where it has all of the control input points here and then just a time at the end. But now we have a lot more in multiple shooting because now you have a whole bunch more states in your multiple shooting formulation, a whole bunch more. So we can't just say the number of force points is equal to the number of elements here minus 1. Get rid of that thing, right? We also have to get rid of all of these things. So we got to say here, num L W divide, so we're going to minus 1. So for instance, we had minus 1 right here, right? Knocks off that. Then the remaining elements here, we want to know how many force points there are. We got to divide by 3. Okay, the number, so divide by 3. Because there's 2 states that we have to ignore here. We only want the force input points, okay? All right. So we divide by 3 because only a third of the remaining decision variables we say, how do we say it? So our control inputs. We want to know how many spline points there are just based on the size of the decision vector. So if you're curious why we're dividing by 3, that's why. Okay. So then when you say, hey, our force vector is equal to W1 colon n, hey, that's the first n, not the first all of these, right? Those are not all force points, okay? All right, just caught a little error there before we even finished, all right? So now that's in simulate multi, of course. All right, now I'm back to non-Elcon multi, okay? Scrolling down. So we can send in a W, we send in an initial state, and we send in a time span. So we got to define these things, okay? So W is already sent into our nonlinear constraint by default. You have to send in your decision vector, okay? So we need to define inside of these shots, hey, what's X0? Okay? That's the initial state for this shot, right? So it's the initial state for this shot. Okay, so and there we have how many states in our problem? There's 2 states. Let me pull it back up here. State vector somewhere around here. I think it is. There it is. X of t, S of t. So S of t and S dot of t. Great. So if we want to know what for shot number 1, what is the initial condition? Well, we need to go into our decision vector. It's going to be S1 and DS1. If we are on our second shot, the initial condition is going to be S2, wherever that is, and DS2. Okay? So if we want to know if we have a indexing iter that starts with 1, okay? All right? Then that means that the first S1 is going to be n plus 1. That's iter, right? So we would say that it's of the decision vector, it's the nth value plus iter. Okay? That's going to be S1. 1, 2, 3, 4, 5, 6, 7, 8, n plus 1. And if it becomes the second shot, it'll be plus 2, up to n, right? Now for DS1, it's going to be n plus iter, so 2n, okay? So W, we want of the decision vector, we want 2 times n plus iter. That's the initial state for this shot. Okay? Now, the time span. Okay? Right now, you leave it blank, and this is the time span of this particular shot. Any questions so far? Following along, kind of? All right. And this isn't Python. Let's put a little end at the end here. Okay. So our time span, we want to know what is the time window here that we, like, if it's for the first shot, it's that, right? For the second shot, it's that, right? For the third shot, it's that. And so on and so forth. So that means we should get a list of all the time points and then give it for the first shot, those 2, and then for the second shot, those 2. So let's make a little time vector. I don't think we have a time vector in this function. So that's the final time. Let's create a time vector. And the easiest way is to say, hey, we know there's n points, and we know that the final time is tf from the decision vector here. So we'll say lin space. So linear spacing from 0 to the t final, n. Okay? So if we want to know our time span, which is going to be giving it the beginning point of the initial time, and then the final time of that shot, right? On the first iteration, it's going to be t vector 1, t vector 2. Second iteration is going to be t vector 2, t vector 3. So it's going to be iter and iter plus 1. So let's do time vector iter, comma, time vector iter plus 1. Okay? I forgot a little semicolon there on the line below. So the semicolon, so that way, all right? All right? Okay. This should give on any given shot, it should say, hey, shot 1, it'll tell me the final position and velocity after that shot. Then the final position and velocity after that shot for all shots, okay? Now, in order to send back in our code our GEQ, our constraint, our equality constraint, it needs to be satisfied when it equals 0. All right? So what we need to do is take this and compare it to our next initial condition here. Subtract them, and if they're 0, you're good, right? And that becomes a constraint that's added to our list, to our vector of equality constraints. So what we're going to do is we're going to create a vector that just gets that's bigger. Okay, it's big enough so it has a defect constraint. So you want we'll call it a defect constraint, which would be the integral of, let's call it just time of shot 1, okay, of x of t dt for the time of shot 1. Let's make this bigger so you can see it a little easier, okay? This is just some hand-wavy math right here. Basically, that's that little integral. That's your simulation, right? Okay, minus x2, right? So that's the state at time 2, right? Then you would have the integral of cross shot t2 of your dynamics dt. And you say minus x3. So for your, and keep in mind you have 2 states in x, right? Okay, so that means that you would have 2 states, all the way to your final shot, right? So on each shot, we will want to check two states. We have 2 states that could be that could be wrong, that could not obey physics, right? So if that's the case, we need to make a set of constraints. I'll call them defect constraints. Let me move this down. Defect constraints. It's going to be a vector. I'm just going to initially populate it with zeros. And what size does it need to be? Well, I'm glad you asked. It's going to be the number of shots that you have, and shots times 2. You have 2 states to check the defect for each shot. Okay. Right. So we have this thing called defect constraints. We are pre-allocating it, meaning making it the right size, pre-allocating. And now we're inside the loop. We can add in the result of each of those defects, right? So we're going to take the result. So we're going to say defect question. Oh yeah, you do. Thank you very much. I missed that. We would do a comma 1. Yes, because we don't want to. Because if we didn't define the other dimension, the question is, don't we have to define the other dimension? We do, unless we want it to be a square matrix, which we don't. So I just screwed up. Okay. In Python, you don't have to, and then it just makes anyway. So angry with myself. Thank you very much, Marco, I believe. Okay. So comma 1. Thank you. All right. Defect constraints. Okay. So now each of these defect constraints, we want to change each of these depending upon the shot that we just did. So if we're on the first shot, we're going to say, hey, we want entries number 1 and 2 of our defect constraint to be the result of our simulation minus our next decision variable, okay? So if we are on shot 1, we want 1 and 2. If we're on shot 2, we want 2 and 3. Okay. So we're doing some kind of clever math index, just little clever math indexing. There's other interesting ways to do this. I'll show you how. Hopefully, if we have time today. But this way, I'm saying, hey, if I am on the first shot, I want it to be. So it's going to be iter. Say 2 times iter minus 1 colon 2 times iter. Haha, that works, right? Because if I am on first iteration, 2 times iter is 2, minus 1 is 1. Then if you're on the first iter, this is 2, 1 to 2. If you're on the second shot, 2 times 2 minus 1 is 3, 2 times 2 is 4, 3 to 4, okay? This just files it in that, the first 2 elements, second 2 elements, third 2 elements, right? Just being a little clever with math there, that's all. All right. And then we want to say, oh, each of those elements, it's equal to, that's going to be our final SF. So SF minus whatever the next, let's go up here, whatever the next initial condition is going to be. And that's going to be, let's say, S2 and DS2, right? And we did that math right here where we said WN plus iter, right? Okay. So this is going to be WN plus iter plus 1, because it's the next one, semicolon. Then we grab this thing. It's going to be N plus iter, this is 2N plus iter plus 1. Okay. This is just saying, hey, this is the initial state for this shot. Okay. These are initial states for the next shot. In fact, let's lay that out a little more cleanly. So this is going to be initial states. So if we say that, let's call this S next is equal to, and I'm going to grab this. Okay. I'm going to say this is going to be the initial state for the next shot. And then it's going to be DS next for the next shot. So this good, and that'll just be this element right here, right? Okay. That's going to be initial state for the next shot. This is the initial S state. This is going to be the initial DS state. So then our defect is going to be our final state from the previous shot minus the initial state from the next shot. And then the final state from the previous shot for your velocity minus DS next. That's for the next shot. Okay? Now that should file everything into those defect constraints. Okay? It'll do all those simulations, then I'll run them. Okay? So place each defect constraint in a vector. Okay. And you can see how if these are subtracted from each other and if they're equal, that's great. Then that means that we have successfully aligned the end of this shot with that. Okay. Now, the defect constraints are not the only constraints we have to deal with that are, so what we could also say is we also need our initial conditions. Constraint. Meaning that we're going to need our initial, we need our drag racer to start at distance 0 and velocity 0. Okay, and given that it is a decision variable that we have there, okay, which we have right, that's going to be decision variable n plus 1, and this is decision variable 2n plus 1. We have to say that they're equal to 0. So we're going to say wn plus 1 semicolon w 2 times n plus 1. Okay? That's the initial condition constraints. Okay? Meaning that if these are 0, the constraints are satisfied. Beautiful, awesome, cool, great. Now we also have to have our final condition constraints. So final condition constraint. I'm having very verbose, long variables here. Why not? Okay? And that means we want it to end at the final position, right? So our final position is a decision variable here, Sn. That's going to be at, this is the 2nth variable, 2n right there. So this one right here is going to be 2n minus 1 for that position. And this is going to be 3. This one right here is 3. No, wait, no, this is just 2n. Sorry, this is just 2 times n. This is index 3 times n. That's easy. Okay. So we would say our final condition constraint is that w 2 times n, it must end where? It's got to end at our final position, S final. S final. So When that's 0, that means that our final position is at S final. And our velocity, W 3 times N, when that's 0, it's satisfied. It comes to rest. Okay? So we have defect constraints. We have initial condition constraints. We have final condition constraints. They are all equality constraints, right? And we got to tell F min con the value of our equality constraints. I don't know why I made these capital G's. I'm going to change these to lowercase g's for my own sanity. Lowercase g, lowercase GEQ up at the top of non-Elcon multi. We've already said there's no nonlinear inequality constraints, right? Well, we have to put all of our equality constraints in just a big vector, and that's easy. Watch. We'll say that, we're going to say that G is equal to defect constraints, semicolon, initial condition constraints, and final condition constraints. I apologize for making it so long. I'm going to do a little dots, little ellipses to put them on different lines. Okay? They're all column vectors, so I'm just appending them. I'm adding to the end. Column vector, column vector, column vector, all the way down like that, right? And that should be GEQ. GEQ. So we concatenate, just means you kind of add them to each other at the end of each. So you concatenate all our column vectors together. You'll notice I was careful to make this a column vector, this a column vector, and where is this? Yeah, and this whole thing was a column vector, and this whole thing is iterated as a column vector. All right. This programming language is MATLAB. We are doing multiple shooting. Check out the previous live streams. All right. Right. So we got that. So awesome. So that should be everything we need in non-Elcon multi. If we go back to my good old little org chart, this little organizational chart, I think we're ready to go. We just have to now have F min. Oh no, I'm losing everything. Oh my gosh. Who knew I could be so klutzy? All right. We have to have F min con, call cost, and non-Elcon multi. So let's go do that. So let's go back, and that's inside of which function here? The drag race multi for running our little drag race racer. Okay? All right. Let's do some constraints. So, well, let's call F min con. What are we going to need? Right here, we're going to need our cost function, F min con. So our W star, which is our optimal decision vector, is going to be equal to F min con. And our cost function, which we called cost, we defined it right here. It's just the last element of our decision vector, which we all know is, we decided is our final time. Woo. Right. Now we need our initial guess. Okay. So our initial guess, x0, which we have not defined yet, we'll call it w0 because we like w's for our decision vector, w0. And A and B in matrix, those are inequality linear constraints. We're not doing any of those. We don't need any inequality, any equality linear constraints. Open, close, giving us little hints here, right? So we have 4 open closes. A lower bound and upper bound, we do need those because we have a force limit, okay? So LB and UB. Okay. Right? So LB and UB. All right. And we have our nonlinear constraint. Well, guess what? It's called non-Elcon multi. Oh, did it not take in W? For some reason, it doesn't take in W. I don't know why I don't have that. I went back to non-Elcon multi, and for some reason, W is not there. All right. Yeah, but the volume, and maybe just turn it up a little bit. I don't want to blow out my microphone here. All right. So, all right, W. So non-Elcon multi, we need to give it its nonlinear constraints function, and because it's not a handle yet, we have to say not, sorry, at non-Alcon multi. Okay. And we can also add options here, and those will allow us to add iterations. Okay. We'll do a little semicolon. We'll leave it open. Well, we don't need a semicolon just yet. So what do we need to define? W, 0. Okay. So we need our, which is our initial guess of the solution. Okay. All right. So it just needs to be a bunch of numbers that we think are a decent guess. How decent, we'll see. But it has to be the right size, right? And we define the correct size by saying, hey, we have n spline points. And if we have n spline points, our decision vector is going to have 10, n plus 1, right? 3n plus 1 variables. So we'll say, and I recommend whenever you have time, final time as a decision variable, don't make that initial guess 0. Okay? Don't guess 0 time. That's probably going to be a bad local minima. Okay? But if you give it anything positive, you have a much better chance. So I'm just going to say they're all 1s. I'm going to say 1s. And it's going to be size 3 times n plus 1, right? n, 2n, 3n plus 1. They're 3n plus 1. This is great, because if I ever change n, it automatically updates this, right? Okay, awesome. Lower bounds and upper bounds. Okay, this is a vector that has to be the size of our decision variables, right? It has to be the same size as that, right? And if there is no lower bound, you want to tell it the lower bound is negative infinity. It can go as low as you want, right? So by default, I'm going to say that it's going to be minus infinity, and it's going to be the size of W0. This is just a little trick where this gives you the size of your initial, the size of your decision vector. Okay? If you're interested in Python, it's 1230. Okay? All right. So, all right, fantastic. It'll be good to have you. All right, so let's see, W0, and then it creates a bunch of negative infinities of the correct size. All right, in fact, actually, I don't. Watch what happens, okay? So let's say I create W. Let me just run these lines of code here, okay? I'll show you how it works, okay? Someone's saying I need to have a second dimension here, okay? I'm going to run these lines of code. So I've just created W, all right? W, on W, on that one. Sorry, I thought you meant for this. Yes, I need some extra dimension there. Yes, is that what you meant, Marco? Yes, okay, you're correct. I thought you meant for this. We do not need it. Okay, yes, we do need it for that. Thank you. You are correct for that. So we need to add a comma 1 here, right? Okay, but down here we do not need it. So if I run all these commands right here, CLC, there we go. So W0 is just a big series of 1s, right? And this size of W0, that code I'm just copying, what does that give you? 31 by 1. So if I run this command, it creates a 31 by 1 of negative infinity, right? Cool. The only thing is, so by default, they're all negative infinity. And when we're done, okay, so now we have to, so they're all negative infinity, except we want our force points to be limited, okay? So we want an F min, which I believe we said is minus 10, and an F max, which is positive 10. So we want the first n of these bounds to be minus 10. So we're going to say that LB 1 colon n, the first n points, those are the ones in our decision vector, okay, are equal to F min. What I'm going to do is I'm going to comment this out so I can just run this script. I'm commenting it so I can show you how it works. Should work okay? Look, first 10 elements are negative 10 of LB. Now I'll do this exact same thing for the upper bounds, UB. These are the upper bounds on each of the decision variables, UB, F max, and positive infinity. The upper bound should be positive infinity. And except for the ones, the first n of them should be f max. Let's make sure that works. So if I run that without the semicolon, my upper bounds, the first n of them, which is n is 10, is f max, okay? And when we're done, this should hopefully do a nice trajectory optimization showing us how to go really fast, to optimally drag race your vehicle. You stomp on the gas and you stomp on the brake. That's what we should see in the end, okay? Now, the only thing we've got to set the options, okay? So what you say is this option structure is equal to optim options, okay? You want to tell it, hey, I want to using fmin_con. And what I specifically want to see is I want to see the display of the iterations. Display iter. We've done this before, okay? All right. And that should be everything. And I can uncomment this, and we can cross our fingers. Very scary, my friends. Okay? I'm going to run it. I should see a bunch of iterations. Let's see what happens. Wait, give it a second. I'll swig my coffee. Oh. Things are happening. Something's happening. Not sure what. Okay. What I'm seeing here is I'm seeing this column here. This one, oh, it probably errored out. It said converged to an infeasible point. So something bad happened. Okay. So right here, it's saying this column that says feasibility. It's 10 to the minus 1. That's like 0.1. That's way too large. We want that number going down to 10 to the minus 6. So something is going wrong. Okay. So let's take a look at what happened with the solution. Right now, it tells us converged to unfeasible point. It didn't solve. That's not solved. Just because it ended, it doesn't mean it's a good solution. And you can tell because it's infeasible, because this number in the feasibility column is way too big. We want like 10 to the minus like 9th or 6th. Like, yeah, so something's going wrong. And here, but it spit out the values minus 10. Oh, I think I know what happened. Wait. F max. No, F max is right. Okay. It, for some reason, made all of our points negative. And the time, this final value, at the final time, that's a really small final time. Okay. My guess is that we need to increase the initial guess for the final time. Okay. So our initial guess here, we're going to make it 10. We're going to make, instead of making ones, we're going to make it a whole bunch of tens by just multiplying it by 10. That's your initial guess. Let's see what happens. Run it again. Oh, yeah, we're doing better. I'm looking at this number right here. I don't know if you can see my mouse. 10 to the minus 5, 10 to the minus 4. Yeah, we're in good shape. It's gonna get close. Okay? 10 to the minus 6. Okay, it's probably going to be feasible by the end of this, unless it starts running out of function iterations, which we can let on the left side. It says right over there, over that you can see. That number can hit a limit that we can always raise, okay? Now, just because it solves doesn't mean that we did it right if it does in fact solve. 10 to the minus 12. Oh, yeah. Oh, yeah, it's going. It's going. The solver is finding ways to make it feasible. So feasibility is only part of the equation, though. Okay? Look, the solver stopped prematurely. What happened? It exceeded the max function evaluations 3,000. 3 times 10 to the third. Okay? It's right over there. That's the number of... So we went over 3,000. We're done. So while it was super feasible, this value over here was only 10 to the minus 1. That's the first order optimality, the first order necessary conditions, hitting the bottom of the gradient. Okay, we want that to be even smaller, 10 to the minus like 6. Okay, so let's just give it some more iterations and see what happens. Okay, let's go to, so we got to set the max function evaluations, and that's under options. So we want to say comma max. Let's give it a new line here. Dot dot dot. Max function evaluations. And instead of 3,000, let's do 10 E3 or 10,000. Okay, let's run that. All right, we're running it. So the fact that we're getting something that's feasible is a preliminarily good sign that we've done this right. You'll notice this is taking a bit. We're doing multiple shooting, not because it's good for this problem, what we already solved with single shooting, but it'll be more helpful with problems that you can't solve well with single shooting, ones that are nonlinear, unstable, underactuated. It's better for it. Okay, look, 10 to the minus 7, 10 to the minus 11. Oh, yeah. Okay, the solver's finding ways to make it feasible. Great, descending the gradient of the constraint, descending the gradient now of the optimality. So now it's going to try to knock down this number here on the right. That here is your first order optimality. You can see, look, first order optimality, okay? Right now, it's 1 or 10. So it's moving around. It's using, I believe, an interior point solver to try to fix it. Let's watch it go. Come on, guys. Because I want to see what the solution looks like. Make sure we're doing it right. Because it's still possible we have a mistake in our code. And I'll show you how we're going to check. All right, it's moving around. I have a feeling it's gonna iterate out because we're already at 6,000 iterations. Okay, and it's not getting terribly closer. Let's see here. So it could be a couple things. One is there's some problem in our problem setup, or we need to do a different initial guess. Okay, 10 to the minus 4, 10 to the minus 5, 10 to the minus 7, 10 to the minus 9. My hope is that whenever this finishes, we get something that's feasible. And then we can look at the solution. We can plot it. We can plot the the force trajectory. Oh, okay, finish something. What did it do? Local minimum possible. Constraint satisfied. Okay, that is the second best answer we could get. The second best. The best is local minimum found. So it's saying, yeah, the constraints are satisfied. Look at that number for your constraints. Very small. But we're not sure we're at an actual local minimum. This number, 10 to the minus 1, that's like this is like 0.229. That's pretty big in the scheme of optimality tolerances. So that's what I'm looking at here. So we have a solution. I would like to see what that solution looked like. And actually, I don't like it very much. Yeah, I have a feeling there's some kind of error in our code. That's probably what's going on. Because what I'm going to do is I'm going to create a plot, okay? So I'm going to go into my code. I'm going to create a plot. We're going to plot the resulting forces and states. So I'm going to create a subplot, which is going to have our one force and our two states over time. So subplot 3, 1, 1. This is a 3 by 1 subplot. So the top one is going to be our force points. So that's going to be, so we're going to plot, let's just plot our force points. They are, oh, whoa, friends. I think I found what our issue is. This is our optimal decision vector that's found so far. Is that number positive or negative? It's negative. It's negative. What does that correlate to on our decision variable, our decision vector? Time. It's time to trying to time travel back in time. How do we prevent that? We make sure that we have a lower bound on time that doesn't go to negative infinity. We can add that really easily by saying, hey, our lower bound on the very last value, instead of negative infinity, it's 0. Okay? If we need to make it slightly above 0 later, we might do that. So time must not be negative. It got stuck in a negative time. This is for a controller for a very simple drag racer. So you can check it out. The last multiple shooting optimization. Okay, all right, let's see what happens here. I'm looking at the feasibility. See, the feasibility is ticking down, getting smaller. 10 to the minus 2. I don't know if you can see it right there. Boom, boom, boom. 10 to the minus 2, 10 to the minus 2, 10 to the minus 2. Okay, it's not getting any smaller right now. What's going on here? Still a very small time. Why is that? So it's going negative, negative 10, negative 10. Clearly it's infeasible. But let's take a, oh, I forgot to plot everything. We got to plot all these things. Let's plot what comes out when we're done. So we're going to plot all of our force points. That's of our W star. That's the first n points. Okay. All right. Then we want for our second plot 3, 1, 2. What's the little title here? These are our force points. Okay, 3, 1, 2. We're going to want all of our positions. So plot W star, that's going to be n plus 1. That's going to be through 2n. Those are all our positions. 1 through n plus 1 through 2n, 2n plus 1 through 3n. Okay. These are our positions. And subplot 3, 1, 3. We're going to plot all of our velocities. W star n plus 1, 2 times n plus 1 through 3n. And it's going to plot all those values. Just to see what those are, I'm going to copy these into my... Okay, what do I see here? It looks like to me all my force points are at negative 10. That's not good. I don't know why it's doing that. And here we have it's going up, down, like that. Let's try our initial guess. Let's try an initial guess of 5s, just to see if that makes a difference here. Okay. We're going to change our initial guess to 5s and rerun it. What am I looking at? I'm looking at feasibility. Okay. And while this is a slower way to do trajectory optimization right now for this drag race problem, it will be more effective for nonlinear problems. Okay. So for nonlinear unstable problems. All right. We're still getting stuck somewhere. You can tell because the feasibility is not going down. It's going to yell at you. Okay. Why is that? Why is that? It keeps going to negative 10. Something ain't right. Okay. So let's go and try to figure out what's going wrong here. What I might recommend, we check our nonlinear constraints. Go to nonlinear constraints. They are called non-Elcon multi. Okay, let's pull that up. Non-Elcon multi. What could be going wrong? So we have the number of spline points, number of shots, time vector. All right, scrolling through here. 2n plus iter initial state for this shot. Yeah. Okay. What we might want to do is check to see what happens when we actually simulate each of these shots. What's actually what this little fancy plot we have right here. Where'd it go? Let's actually generate that for our real problem. Okay. All right. So let's go back. Part 2. So once we are done plotting, we want to actually simulate each of these problems. So let's do that. Okay. What we're going to do is we're going to let's simulate each of our shots for plotting. Yeah, here's what we'll do. Okay, I'm going to put this down below. So if we want to simulate each of those shots, okay, we're going to need a couple things. We're going to need a time vector. So we're going to create a time vector of our solved control inputs. That's these. And it's going to be a spline with TF at the end there. So that's going to be a time vector. It's going to be a lin space with endpoints from 0 to T final. So that's W end. That's your T final, right? In fact, let's actually call this. You know, T final is equal to W end. Let's call it out, right? W star end. Okay, the optimal decision value. Okay. Yep. So yeah, for those people jumping in, you're on lecture 14 of a class, by the way. Just so you know. We're in the middle of doing multiple shooting. All right, so here we go. We've got TW star. So that's going to be a final time. Okay, let's get all of our force points. Our force points, that's going to be W star, our optimal decision variable, decision vector, 1, colon, N. And we want all of our S points. That's going to be W star, N plus 1, colon, 2N, right? And all of our DS points for our velocities for this car moving forward, trying to get this car to stop on a dime, W star 2 times N plus 1, colon, 3 comma N, 3 times N, right? Okay, so that's going to be all of our points. So if we want to actually plot these things, I'm sorry, I'm going to move this, it has to move it above our plot. I'm going to grab this and move it above our plotting. Okay, that's going to be our T final, F points, S points, DS points. So now I can actually write this more simply. I can say I want my time vector. Oh, it's going to be from 0 to TF with N points, right? So I can plot my time vector. F points. And I'm going to make it black line with an X's. So it's going to have little X's. Or, you know, here on this little thing, I have little O's. Make little O's. Happy little O's. Lowercase o. Okay. So that's, and then we're gonna plot over time our time vector for our position points. That's our S points over time. S points. Let's make that also. Okay. Oh, let's just make that black X's, no lines, just X's. I think that we'll give it a line for now. I'm just a little concerned. Okay. All right. And then finally, we want our velocities. So those are title velocities. Velocities. All right. This is in meters. This is going to be meters per second. By the way, you are also learning the process of debugging these programs. Okay. You'll notice a couple of tricks that I'm using. And so, all right. So we're going to say time vector. And we're going to have DS points. And it's going to be K. We'll make it K. K for black, line with X's. All right. And if I did this right, if I run this, it'll rerun the whole optimization. And at the end, it'll have a more thorough plotting of what the optimization thinks is the best answer it can come up with. The amount of force you would push on this car that's moving forward, the position of that car over time, and the velocity of that car over time. Right now, I'm looking at feasibility, 10 to the minus 2. That's bad. Just like before, it's probably going to run exactly as before because we changed nothing about the optimization. But I'm looking at that. That's bad. That's not working. There's something going wrong. But I can have a little better plot here. It says that my force points are all -10. It's trying to make my car move forward. It thinks it's trying to make my car move forward, but it's just not. So this could be something with the simulation. So what I'm going to do is, like I talked about, is I'm going to try to plot these little squiggles here for where the shot thinks it's going. Okay? So hold on to your hats. Let's do that. Our goal today will be to fix this multiple shooting, and then we'll be done for the day. Okay? Then we can move on to direct collocation and other fun things for next week. Yeah, we should finish up direct collocation next week before spring break. Oh, that'll be fun. Then we can do more. Oh, then we'll do Lagrangian mechanics after spring break. Oh, I love it when we get to Lagrangian mechanics. It's going to be fun. All right. Okay. So we want to plot. Now, let's simulate each of the shots. Okay. And plot their trajectories to see if they make sense. We got to figure out something's going on somewhere in one of these codes, right? So let's plot those. So we're going to need to loop iter 1:n-1. There are n-1 shots. Okay. And thankfully, we do have a simulate multi tool. Okay. The only problem is, I will say, is that it only sends back the final position. I would love to send back the entire trajectory. We can do that, okay? So the simulate multi-tool is exactly what we want to use. But I want to send back not just the final position, I'll also send back the entire trajectory, which is T out and X out, which we can do. That's not a problem. We just have to add here in our outputs, T out and X out. That's it. This is all in simulate multi. Okay. But it also means that we have to go into non-all-con multi, and it needs to be prepared that whenever it runs this simulation, it's going to, instead of receiving these two variables here in non-all-con multi, we need to be able to receive other stuff. We could say, oh, T out and X out. Okay, but you'll notice that we don't use T out and X out inside of the non-all-con, right? So there's a cool trick. You can just say tilde, where it receives it, but it ignores it. Okay. All right. So now simulate multi. Second here. There you go. Now simulate multi is going to send back each of these little trajectories whenever we simulate a little multiple shooting step, right? So let's see what happens. So we're going to go back to drag race multi. And so now we're going to simulate each of these shots and plot their trajectories to see if they make sense. So for shot 1, we're going to want to do, what is it? We're going to say it'll give us S, SF, DSF, T out, and X out. And simulate multi. What is it? It's just W, X, and 0, X0, and time span. Yes. Okay, grab that. W, X0, and time span. Okay. Now, X0 is the initial state. What do we do for this? Let's go back to non-all-con multi and just grab what we used there. Okay. All right. We used this. Okay. These two lines. I'm going to grab those two lines in non-all-con multi. All right. Now let's put them inside of our shooting loop. Okay, I just copied them in. All right, that's the initial state for this shot. All right, the only difference is not W, it's W star, which is our optimal value, right? W star. Time vector. You have the time vector, iter, and iter plus 1. That should be fine. Then we're doing simulate multi. That should work. And now that for each of these shots, I want to plot the shot on the right axes. Okay? So I'm going to say subplot 212. That's the position subplot, right? Okay? And I want to plot that whole trajectory. I don't want to blow away the entire plot, so I'm going to say hold on. I'm going to plot T out and the position X out, which is going to be the entire first column. So colon, comma, 1. I'm going to make it a black line. Okay? And then, hold off. Then I'm going to go to the next subplot. I'm going to plot all the velocities. Sorry, this should be 312. I apologize. 312. Here's our 3 by 1. This is our third subplot. We're going to hold on. We're going to plot T out, X out, colon, comma, 2, because it's our second state. Make it a black line. Hold off. End the loop. So I'll make this big so you can see all of it. And we're going to watch what happens to each of these shots. Okay? This should take the previous plot that came out and then just start simulating and then throwing trajectories up on the board. Okay? Let's see what happens. Okay, I'm going to run this and let's, oh gosh. Can't see what's happening. It's going to be the same optimization. Take a second here. Let's see anything. Oh my gosh. Please let me. Okay, thank gosh. All right. Again, same thing. You'll notice that it should be behaving exactly the same way, the optimization, because we didn't change anything about it, and there's no random variables in it. Okay, I've screwed up something. W. Oh, shoot, there's a W something. W star. Right here. W star. Forgot about that. Oh, my goodness. Let's just clear everything. I don't want to rerun everything. Whatever. I should have a separate script just for plotting. That way we don't have to rerun the whole optimization. Thankfully, it's not that long. Okay. One thing we could do to make it run a little faster, or at least end faster, is we change the number of maximum function evaluations so it's smaller. Okay. Yeah, it should hit all right. Okay. All right. Oh, okay. Okay, friends. I'm looking at this and I'm seeing an issue. I'm seeing a problem. Okay, I can tell you right now. So here you can see the little black lines that are the shots. They in no way line up, trying to line up with the next shot. There's something going wrong with, I think, our simulation. How do I know this? Because for one of these shots here look at the velocities. It's flat, okay? But it should be applying, according to it, negative 10 newtons. So it should be trying to decelerate this thing or decelerate this thing in the negative direction, and it's not. So there's something wrong with our simulation. Something is wrong there. There's probably some simple error we have in our simulation. So let's go back to simulate multi. See what's going on. See, simulate multi takes in, oh, I think I know what it is. ODE fun. Takes in W. It's its own function here. File. Yep. There's the problem. There's the problem. ODE fun. So ODE fun takes in W, your decision vector. And this was written for our single shooting method. Okay. So it's computing N wrong. In single shooting, you only have N plus 1 decision variables. In multiple shooting, we have many more. So we have to do the same deal where N divided by 3. This is all in the ODE function. Okay. Technically, this might have broken the single shooting, but that's in a prior folder, so I'm not too mad about it. So I'm going to try running it again. Drag race multi. Okay, something happened. X and V must be the same length. Okay, I think I know it's there's something going on in ODE fun that I broke. Okay. N divided by 3. W. T end. Doesn't like this. Ha! Here we go. U list 1:n. This line right here, line 7, 1:n. It wasn't this, the U list was not the same size as the T list, so when we're doing the interpolation, these weren't the same size. That's what it's yelling at me about. Okay, interpolation wouldn't work. Save it. Okay, we change this to 1:n right there. Let's go back to drag race multi. Let's run it. Okay, I'm liking it. Oh, look at this, friends. Look at this. Oh, it was hitting 10 to the minus 4, 5. That's good. That right there, you can see the feasibility right there. We're getting, oh, and the first order Mally is getting fairly small too. This is looking good. This is looking positive, friends. Okay, then when we're done, we'll see how it plots. Okay, yeah, look at that. Look at that. 10 to the minus 7, 10 to the minus 9, 10 to the minus 7. We got it. We got it, friends. Holy moly. Okay. Local minimum found that satisfies the constraints. All right, baby. All right. We did it. Okay. Oh, can I show W0 again? 1018. That was a little while ago. I'm sorry, Cricket. I apologize. So let's see. W0. It's 5 right now. I think it's going to be fairly robust. There was an error in it. That's why it wasn't working so well. It probably had very little to do with my initial guess. There was error in my code. Let's take a look at that beautiful plot, friends. Okay. Force points. How do you optimally drag race a car? Slam on the gas. Slam on the brakes. I figured it out. That's the force. Okay. Here's the positions over time. You can see the comparison. Oh, look at that. That looks gorgeous. And look at, there's the velocities over time. Oh, so good. I'm just going to change a little bit to the plotting. Okay. And change a little bit about the plotting. I don't like the fact that I'm plotting dashes here. Okay, I'm going to get rid of those. And I'm going to change my initial guess back to just ones. Okay. I'm going to rerun it. We did it. We did it. We have fixed our multiple shooting code. Now works great. So all that futzing around I did with the initial guess wasn't important. My optimization wasn't working. There was a bug in my simulation. Okay. Look at that. I'm looking at here 10 to the minus 4, 10 to the minus 6 for my feasibility. Optimality is getting small too. Yeah, we're going to get it. We're going to get it. Oh, glorious. Let me get rid of this out of the way. For some reason, yeah, the force points. Okay, you can only see the O's up there. Let's make everything a little thicker to make everything easier to see. And just run it again. We have it. We have it working. Let's put a little dash there. We want that. Let's make the line width larger. Let's make it 3. And marker size. Let's make it larger. Let's make it like 10. And that marker size, let's put that for the other ones as well. Marker size 10. I'll leave that up while I rerun my optimization just because I want to see it again. So what were the techniques that we did? Because we had to debug because the optimization just didn't work. And why? Okay? And that's going to be part of homework 3. Is you're going to have to be able to debug your optimizations. Not everyone will have to do multiple shooting. The grad students will have to do multiple shooting. Okay? Oh, look at that. Oh, look at that gloriousness. On, off. It's a simple answer, but it's the right answer. Here's your position over time. It coasts forward, then it coasts to a stop. Where does it stop at? Exactly at the end of the race, at 1 meter or whatever we defined it, right? Oh, look, here's the velocities. It's accelerating, and then it's smoothly, oh, look, comes to a stop. Glorious. Cool. Nifty neato. All right. Glad you found the issue, friend. All right. Cool. Hey, we did it. That's basically the end of lecture, okay? So let's just because we have a second, I'm going to make all the line widths 3 just so we can see a little easier, okay? All right. Now, we did not have to do much in the world of animation here. We could animate this thing, have the block go from point 1 to point 2, right? But what I'd rather do next time is we're going to use direct collocation, okay? And the drag race problem is fun. It's simple. We know the right answer. So we know when we look at it, our code is working. Like that is the right answer. The minimum time way is just slam on the gas, slam on the brakes. But I want to do something a little bit more fancy. Okay, look at that. Glorious. Cool. All right. So we'll come up with a new problem for Thursday of next week. On Tuesday, we will have a normal lecture in person where we already talked about direct collocation in general, but then I'm going to show you what happens when you do direct collocation with linear dynamics, okay? And what happens is that the optimization can become a quadratic program, meaning it'll run really fast and a lot more reliably than even this, okay? Which means that you can run it in real time. And that's what we call model predictive control. It's a really fantastic technique. And then on Thursday of next week, we will code up direct collocation. And then we will probably take a little hiatus. We will start moving, I would say, toward the multi-body dynamics, so Lagrangian mechanics. So we're teaching you how to actually create the physics of a robot or some kind of mechanical system that's pretty complicated so you can then control it. That's what we're going to do today. All right. And with that, I thank everyone for coming here for class. Good to see you. For those who join on YouTube, it's good to have you. I know I fully understand this is not the most accessible time. If you're finding me now because, I don't know, maybe I was on television last night. It's probably not the most accessible lecture, but you can go back to the playlist and start at lecture 1. Okay, they're all there. Okay, we'll keep adding the videos to the playlist. If you can't find the video on the playlist, it's on the live page of the YouTube channel that you're on. Anyway, thank you all very much. I hope you have a wonderful day. For those, I'll see you on machine learning at 12:30. Take care.